Confidence intervals. Confidence intervals are intervals that give us a specific range of data rather than a specific number to figure out where we think everything should lie. Sometimes we want to say, hey, we're confident that the rainfall is going to be between 1 inch and 1.5 inches. Okay, so we want to use that as a range rather than saying it's going to be exactly 1.2 inches. It's a lot easier, gives you a little bit of flexibility. Confidence interval consists of two numbers, so one on the left, one on the right, which we are confident that our data is going to fall in between. Now, we are going to use a percentage to describe this. I am 95% confident that the data or mean falls between these two numbers, or I'm 95% confident that the rainfall will be between these particular inches. Now, you can use different percentages. We're going to talk about how we do that in terms of the statistics problems we're going to be looking at. Now, confidence intervals for means. So we've been talking about sample means, standard deviation, we've been using z-scores. So to find a confidence interval where we're confident that everything's going to fall, that the population mean is going to fall between these two numbers, you would use this equation. X bar is the sample mean. Z star, you'll notice that Z has a star with it. That Z star is what we call the upper critical value for the standard distribution. I'll show you how to find that in the next slide. You have your sigma, which is your standard deviation, and n is the sample size. Okay, so all those that we've been using so far, we're going to still use. Key point to this is that you're going to get two numbers for every answer. Okay, so keep that. Now, for confidence intervals, C is what we're going to use for confidence. So if they ever use C equals something, and they put like a decimal like 0.95, that means 95% confidence. Okay, a lot of times they'll write out the percentage, sometimes they're going to write out the decimal. The z-star is going to be used with your z-score table. So suppose you have an 80% confidence. Okay, so 80% is in the center of the normal curve, if you remember the bell-shaped curve. 10% on either side. Since the z-score table only shows you values to the left, since there's 10% on each side, we find out where there's 10% left uncovered. So we would go to where it would say 0.90, that's 10%, and that would be our z-star. Now, in this case, that would be at 1.28, which you could check on your table. So the 80% confidence interval would fall between negative 1.28 and positive 1.28. For the z-star, for these equations, you're only using the positive. So don't worry about the negatives there. There are three common confidence interval numbers that we're going to be using quite a bit. So you don't have to spend a lot of time looking at your table. You can just have them right here. So for a 90% confidence, which means that there is 5% on each side, you would use z-star 1.645. A 95% confidence level, which means there's 2.5% on each side, is 1.960. A 99% confidence level, which means that there's 0.5% on each side, is 2.576. These ones are going to be used the most often, so I want to make sure that you have them available so you don't have to spend a lot of time looking at the chart. Now, if I give you something different than these three, you will have to consult the chart. So occasionally that's going to happen, so make sure you have your charts available. So let's do an example here. So on day 2 of a study of body temperatures, 106 temperatures were taken. Suppose that we only have the first 10 temperatures to work with. The mean and standard deviation of these 10 scores were 98.44 degrees Fahrenheit and 0.30 degrees Fahrenheit, respectively. We want to construct a 95% confidence interval for the mean of all body temperatures. So we only have 10 temperatures to work with. We want to see if with these 10, do we have enough confidence that we could figure out where all 106 would kind of fall into. So let's look at our numbers that we have to have. So our X bar, our sample mean is 98.44. Our sigma is 0.30. We're talking about 10 scores, so that n equals 10. And since they said 95% confidence, where our z-star is going to be the 1.960 that you saw on the previous slide. So now we're going to put it into the equation. So if you look at the equation here, It's x bar plus or minus z star times standard deviation over the square root of the sample size. So I'm just going to plug the numbers in. So 98.44 plus or minus 1.960, 0.30 divided by square root of 10. Now, I'll do that fraction first and get that number. So when you do that fraction, just go to 2 decimal places for that one. Okay, and I'll discuss how we do each one. So 0.30 divided by square root of 10, that's 0.09. When I multiply it with the 1.960, stay with 4 decimal places then. Keep in mind, 2 decimal places for the first fraction. Once you multiply, you get 4 decimal places. So now I've got 98.44 plus or minus 0.1764. So that plus minus, if you remember quadratic formula, you add and you subtract to get the two numbers. So 98.44 minus 0.1764 is 98.26. 98.44 plus 0.1764 equals 98.62. So these are the two values that we have for our confidence. So we can say we're 95% confident that the mean body temperatures for all 106 is between 98.26 degrees and 98.62 degrees. Now, we're 95% confident. Doesn't mean we're 100% confident because we didn't do all 106. But we're reasonably sure that it's going to fall there. Doesn't mean it's true, just means that we're confident about that. Now, sometimes we want to look at the margin of error and the sample size that we need. So margin of error is this. That's portion on the right of the plus minus. The z star times the standard deviation over the square root of n. We want to have a high confidence level and a small margin of error. Because the more margin error you have, the more chances you could be incorrect. Now, to find the size of a sample which will meet a margin of error, we take that original equation, less than or equal to the margin of error, and what we want to do is find out the size of the sample. Because the bigger sample size you have, the smaller the margin of error. Because when you divide by a large number, it makes it smaller. So sometimes we want to find out what's going to be the sample size we need. So you'll be looking specifically for that. And that's why the equation on the right, which is boxed, you need to make sure you write down because you'll need that particular equation to solve the problem. The one on the left is just to show you what it looks like when you start. The one on the right is the one you're going to use in problems. So let's look at the example I have. So say I told you a population has a standard deviation of 17.3. How large a sample must be drawn so that a 95% confidence interval for mu will have a margin of error that is no more than 1.4. Okay, so we don't want to have a high margin of error, so we want to keep things within a certain place. So we want to use that equation that we have, the one that I told you that was boxed, and what I want to do is plug the numbers in. So 95% confidence interval, which would mean 1.960 for z star. We have a sigma of 17.3, and our m, margin of error, is 1.4. So what we're going to do is we're going to plug it in. So notice where I put each number. Notice that's squared at the very end because we take doing the opposite of the square root. So I find out what that is. So 1.960 times 17.3 divided by 1.4, that gives me 24.22. I square that, that's 586.61. Now, remember, when we're talking about a sample size, we're usually talking about either people or things. You can't have 0.61 of a thing. So we just round up. No matter how small that decimal is, you round up to the next whole number. In this case, n has to be greater than or equal to 587. So these are the two types of problems you're going to see. You have to make the confidence interval, and you will have to find the sample size.